Given that we learned about these three inference rules related to implication, either in the goal or in the hypothesis, let's see if they might help us discharge the proof sequence, especially about the two that we formulated before. And let me remind you which two. Second one, which you're supposed to do the exercise to specify it, and the first one. Let's take a look at each one of them quickly. And the first one over here is about proving the MLR events. The refined version of that can preserve the invariant number 4 in model 2. Let's take a look. At this point, it should be reasonable for me just to really give you some guidance about some critical steps for the proof. And for the rest of the details, it should be up to your self-study. Of course, you can always reach out to me if you get stuck in any of the application for the steps or any insight you think you really want to know. And let's start with the sequence over here that we want to prove to begin with. And of course, we got so many hypotheses. And as always, we want to apply the monotonicity rule to only keep the relevant hypotheses. And as I said before, it's really difficult to really give you some rule about how to use this reinforced rule, monotonicity. I would say try to pick some hypotheses which you think are relevant to your proof. If it turns out you have chosen too little, in which case you can always include more and backtrack. And of course, on the other hand, if you have chosen maybe too many, in which case maybe you have chosen too many, but it turns out you're not really using some of them in the whole proof subsequently. In that case, you can still drop them from the initial step. So it's really some trials and errors process you have to go through. And I want to give you some guidance on these two implication rules application. Okay, let's take a look. And for the first one here, you can see to the right of the turnstile, we got some implication. That's why we can use the imp R rule to actually proceed. And in that case, to be more precise, let's see here. So this is the implication over here. And you can see this part over here is the antecedents of the implication. What we can do is we can actually move this one here to the hypothesis. That's what we can do. So that's why you will see that after applying the rule, we only got the consequence left over here. So this is the consequence part that we are keeping over here. So that now becomes the goal. Whereas you can see this part over here, the antecedents is now over here. All right, so far so good. What about the second rule over here, imp out, the opposite way? That one there really involves about applying the modus ponens, which I mentioned before. In this case, you can see to the left of or to the top of the turnstile, we actually got implication and also some predicate standing alone that matches the antecedents of the implication. So that's why we can apply the modus ponens, which will be imp out. More precisely, you can take a look over here. This is the implication, and you can see the antecedents is really matching. You can see these two are really matching. So that's why you can just choose to keep this one over here. In that case, it will be over here. That's the imp out. These are the two steps that might be new to you. So that's why I'm trying to give you more details. But the shocking fact is, later on, when you get to the second branch of the end R, you will see that this particular sequence, shockingly, just cannot be proved. It's unprovable. And we definitely need to study a little bit further about this sequence. But let me write it down so you can remember somehow the first attempt will actually fail to prove this sequence over here. And similarly for the other proof obligation, which I'll mention briefly. Let me write it down. So this will be the outstanding sequence that that's yet to be proved by maybe fixing our model. I'll talk about it also later. Outstanding sequence that's to be proved. Okay, it's really important to understand exactly what it is. Let me put it down. It will be green not equal to red. MLTL equals green. ILTL equals green. And turnstile 1 equals 0, which seems a bit funny because 1 equals 0, we know that it can be reduced to false. In that case, we are really trying to prove the goal false. So this really indicates there's something wrong with our current model as is. That's why we are reaching something that's unprovable. You can never prove false. False is always false. So this is really the one. I'm just repeating here. Just you can try to look at that and try to see how that sounds to you. To really say this sequence over here, that's kind of like a reflection of our current model, is unprovable. You can think about it before we actually move on. And let me just do a final box just to say this sequence over here is something that we're gonna come back very soon. That's the first one. And if you remember the second sequence that we're going to prove, which is this one over here, that one there will be in the second page over here. Similar idea. I'm not going to repeat. You can also try to look at how the imp R and also imp L, these two steps are actually applied. That's something I already explained in the previous sequence. You can definitely try to do the exercise on your own to see if that makes sense to you. Okay, I'll leave them to you. And also, the sequence over here is also unprovable. And this sequence here is basically identical to what we just said in the earlier one, right? Green now equal to red, ILTL, MLTL both green, and we got 1 equals 0 in the go over here, which is false. So it seems like both of the invariants 3 and also 4 cannot be somehow preserved by IL out and also ML out respectively. That's something we would like to dive deeper to see exactly how we can fix them. If we cannot fix this, that means our model is not exactly correct for the refinement. Alright, so let's now try to do some in-depth analysis about why this same sequence in both proof obligation is simply unprovable. We need to do some analysis. Let's take a look. Okay, let me switch back to the slides to go over some bullet points. And our first attempt for these two invariant preservation proof obligation, and remember we're talking about invariant 2.4 and invariant 2.3. It is so important because whatever that's not provable has to do with how the invariant itself is actually phrased. We'll revisit that in just a moment. Okay, so this is the unprovable sequence, which I also wrote down as the outstanding sequence. And let's now try to see what kind of hints we are really being given by the unprovable sequence. To understand the hints, we really have to put relevant pieces of the model together. Let's see what we can do. And let's set up the context again as usual, and then I will try to talk about each of the failed proof obligations one by one. This is the first proof obligation, which has to do with ML out preserving invariant 2.4, which is over here. Right, it's now highlighted right away. Let's say ML out and also invariant 2.4, which is over here. That's the pre-state version, and this is a post-state version in the Go. Right, I'll talk about the post-state version in a moment. Right, you will see why something seems to be contradictory is happening. We'll see. And the second one is about green should be okay. The second one is about IL out and also invariant 2.3. Invariant 2.3 is over here, and also that's the post-state version over here. And I'm going to use a diagram to actually visualize what's really happening, and you can disregard this part over here just for now. That's kind of the counter example I can construct to show to you. But for now, let's focus on only these two unprovable sequence. Okay, let's zoom in a little bit over here. If you take a look, let's say for the first one. Okay, let's see the first one. The first one is about ML out, meaning that we have some car coming out of the mainland. So what we have is, let me just do this. So that means we got some ML outs over here. So this is the ML out that we're actually considering. We got some car. And that's why A plus 1 should be the case, because there should be one car coming out. So that should be A plus 1. And it is assumed that if the ML out is actually enabled, the light over here should be turned green already. Right? That's quite obvious, because we know the driver only follows through the traffic light. That's one of the environment constraints we assume. That means it should be green over here. However, there is something contradictory based according to our model. If you look at invariance 2.4, okay, invariant 2.4, let's take a look. Invariant 2.4 actually tells us if the traffic light on the other end happens to be green, that would mean A should be equal to 0, right? So what does that mean? What we just talked about so far is just one end of the story about ML out. But what about the other end? The other end is saying that if it is the case that the traffic lights on the island side is happen to be green, then it must be the case that a plus 1, the opposite traffic, must be 0. But as you can see, a plus 1, how can that be 0? A is a natural number. Natural number plus 1 cannot be 0. Agree? So we got something contradictory over here. If somehow our model allows both traffic lights to be green at the same time, in that case, having this traffic over here and having this green light over here is going to violate this particular invariant number 4 over here. Right? Because invariant number 4 tells you if the island traffic light happens to be green, the opposite side traffic must be 0. But a plus 1, according to ML out, cannot be 0. That's one contradiction. That's why the sequence cannot be proved. Right? Really make sure you understand what's really happening over here. You really have to consider, number 1, what's really being proved as proof obligation, and what's really the relevant invariance, and what's really the visualization of what's happening over here. We're talking about this side of the story and this side of the story being contradictory. Let me just say one more thing over here. And ILTL being green, that really implies, according to the invariance, A should be equal to 0. However, what we are having over here is A plus 1 and also A equals 0. It seems like these two cannot be true at the same time, can it? Right? So that's why it's contradictory. Having known this, let's now talk about the other one, which is kind of similar, but let's now exercise our understanding again. Let's now talk about the other unprovable sequence over here, which is about IO out, invariant 2, 3, and also there's a post state, right? Let's now visualize this. So we talk about IO out. IO out is really the other direction. So let's say this is the IO out that we are talking about. IL out. And for IO out to be enabled, we know that the traffic light over here must be green. And we know that once the IO out is actually executed, when it really occurs, we know that we're going to have a car adding to the bridge traffic over here. So that's going to become C plus 1. Agree? So that's one side of the story. However, in order to prove this particular invariant 2, 3 over here, let's take a look. Invariant 2, 3 is saying that in order for the opposite side, if it happens that the opposite side of the traffic light on the mainland is actually green, then its opposite traffic C must be equal to 0. That's really contradicting to what we're having now. Let me show to you. Okay, you can see over here the invariance 2, 3, right? Invariant 2, 3 over here is telling us the following. If the main lane traffic light happens to be green, that must imply that C is equal to 0. So this is according to invariant 2, 3. And can we have these two at the same time? C equals 0 and also C actually becomes C plus 1. Well, no, because C is a natural number, plus 1 cannot be 0. So that's why these two are just contradictory. The same argument as before. So these two, C equals 0 and also C plus 1, is contradictory. And let me just make some annotation just to before. And this part over here about A equals 0 is according to invariance 2, 4. Right? Over here, that we just spoke about. And we know that these two are also contradictory. A plus 1 and also A equals 0. So these two over here are also contradictory. Okay, quite much information that's being spoken about over here, but I'm trying to be as clear as possible. You really want to understand why these two proof obligation will actually fail. It fell because for our current model, it is actually possible for these two lights to be green at the same time. In that case, it's simply not possible to prove about the invariance, either for this one here or for this one over here. Right? That's what I need to say. And the next bit is to see why the current model can allow two traffic lights to be green at the same time. It doesn't make sense because it's supposed to be like a one-way bridge. Either you go for this way only, or you go for this way only. It cannot be that the traffic light are green at the same time, in which case you're gonna get some crash having two-way traffic on the one-way bridge. Let's now talk about the final bits to really convince you that the current model really is allowing two traffic lights to be green at the same time. Let's take a look over here. Starting with the initial model where both traffic lights will be red to begin with. Let's say the maximum capacity for the cars will be 2. And what we'll do is we're going to say MLTL green. So we're going to set this light here to be green. So we got some ML out. And then we got some IL in over here. And then we got some MLTL green. We can turn this one to be green. It's also enabled. Because at this point over here, you can see the guard for ILTL green. You can check it. This value over here can allow it to be enabled. And then after this, we're going to say IL out. And also ML out. You can follow through this particular sequence over here to see why all the events are enabled in the trace. And eventually what we will get is we're going to get MLTL and also ILTL, both being green. So this is where the contradiction came from. Okay, so this part over here is really the source of the contradiction that we spoke about over here. Okay, you can think about, I'll try to be a little bit more careful about not to cross the fragment over here. This is one, and this is just another one. Right, I'm not going to waste your time to really read out the values over here, but you can definitely go over this trace over here and then try to convince yourself the state values over here for individual events is actually correct, has been correctly updated according to our current model. And eventually, it is possible to lead to a state where both traffic lights are green. And when both of them are green, so this will be the source of having some contradiction in the goal of the sequence over here. Alright, it's a very important analysis pattern you want to really go over to make sure you understand the detail. I think what I said in the beginning about why these two are having contradiction based on the visualization I made. Just make sure you follow that and then reach out to me if you got any trouble. Alright. The next follow-up question will be, naturally, how do we fix this? We're going to talk about it.